It's like a military base in Cheyenne, and there's like the University of Wyoming. That is, that's it.
They're always like stocked up. So.
I would love to take them.
My buddy was like thinking about going to school there. I was like trying to tell him not to, because like that town is nothing but like a couple college kids and like old people. Everyone there is like at least like 60. He was like, nah, you're full of shit. Like, he was like, I was talking to him over this last break. He was like, yeah, you were pretty spot on. It's not anything here.
My friend would drive all the way from Fort, or he'd drive to Fort Collins, just like do shit.
Yeah, that's on.
Type of band those scripts be
My cousin goes to school up there too. Mainly because my grandma's up there and like it's like in state and stuff like that.
Yeah.
Yeah. For me.
Cheyenne is Frontier Days. That's what the only good thing about.
Yeah. Even Frontier Days though, you go once, you've seen
And then it's
everything.
like, yeah. It's just a big rodeo.
Yeah.
Alright. I think I know what we're talking about today, but just in case. Oh, I got shit to get back to you. It's like a grading machine these days. It's crazy.
It's always grind.
What's that?
On your grind.
On my grind, absolutely. Yeah, like I don't know, grading math is way easier than. Are we recording? Are we rolling?
I think I hit
Thank you.
record.
Cool. This was already graded. Look at that. Oh wait, these are gratitude letters. Hold on, that's something else. Yeah, I think I'm caught up, but I do want to say that there's like you should go look in the grade book and see. I gave this talk in real analysis this morning. Go look at what needs to be made up, or what you choose to make up. Right? You don't have to get an A. You can choose to get a B, and that's cool. There's nothing wrong with a B. There's certain requirements in terms of how many 9s and 10s you need. Boy, Christmas for you. All right, so let's see. But everything that's happened needs to be made up before break. We need to figure it out. So if you want to make something up, figure it out before break. Because the one thing I don't want is like the last week of class to have, I didn't want this for you, and I just don't want it for me. To have to grade the entire semester's worth of stuff in the last week of class. Let's see, semester. So please get on that and send me an email before, like a day before you come in, and then we'll figure it out. If you want to do this tomorrow, then please email me tonight. I'll be in. Oh, I'm so sorry, Kayla. Jeez. I'll be in tomorrow from just 11 to noon. But if you want to take I can set you up at 10. I just have an appointment at 10. And these are just so poorly organized. I mean, it's kind of organized by skill check, but could have spent a little while just grouping these together. And manual. So yeah, so please just get on that. I think I had set like a 2-week limit. Maybe I'd done that. I feel like I did. But I will let you make up anything through skill check 1 just before break. Also, if I think I got a couple. Yep. It was kind of wild. Like in general, the curvature ones that folks turned in, like were really like spot on. And if you mess anything up, you mess something up on the integral one. It's Arnold. Boop. Brandon again. That was pretty good. All right, so I think, oh, then Camille, I got a couple for you. All right, I think that's it. Except for I got Alexander and Athma. Everybody get back everything they expected to get back?
Those 2 skill checks?
Just those 2 skill checks, maybe even just one. If you are still doing, maybe I could collect the other ones from you so we don't forget at the end of the hour. So if you have the curvature one, and if you're still working, you should still be working on it, theoretically. But I am looking for a number. So, oh, thank you, that's cool. Anything you got for me, I love it. Bring it on, corrections. So, a couple of notes. If you are doing like a redo of one of the skill checks, you only have to redo the part that it says redo on. Some people like get perfect on one part and then need to redo another part. Also let me know that. And then if you turn in corrections, you just turn in corrections for the one part. How are we feeling? Are we good? Everybody good? Yes, sir.
Let's go check 3 back. That was the one that you wrote on a separate piece of paper.
Oh.
That one.
There we go, cool. I remember seeing something weird in there. All right, well, let's get rolling. We're gonna start some new stuff today. We're gonna talk about functions of multivariables, and we're gonna talk about limits and continuity, and probably by the end of the hour, differentiability. So let's just start off with the basics, because we need to talk about these first. Limits and continuity, that's a CO, continuity of multivariate functions. This is fun, this is cool stuff, things get crazy. The cool thing is the big leap to crazy happens from 1 to 2 dimensions. And then after that, it's all kind of like the same level of crazy, which is surprising in a way. So let's start off with a recall. We have y equals f of x, good old univariate function, the old every calculus up till now. If I have this and I start talking about the limit at a point, x naught f of x. I'm just going to write that expression there before I write equals anything, because it may not equal anything. So one way to think about this is if I have some function, look, I'm putting a hole in that right there. And that's x naught. I'm going to put a little dot above it. So I've got this function f of y equals f of x and x, and the graph looks like that. What the limit is about, what this is asking is, what output value does this function approach? What is the output value as I get arbitrarily close to this point? It is not about what happens at that point. So in this thing right here, this little example, let's say that that's, we'll call that L1 there, and I'll call that L2 there, level 1 and level 2. So for this function, because as I trace along the graph from the left with my finger and I end up approaching L1, so see, as the closer I get to this input, the closer the output gets to level L1. And as I approach from the right side toward x naught, the output value also approaches L1. So here I would say that the limit is L1. The value of the function at that point is a totally different thing. That's L2. So just take a minute. Is this making sense? You've seen this somewhere in the past. Okay. This function isn't continuous there, but we'll get to that in a minute. But the limit does exist. So for the limit to exist, For this limit to exist, I'm gonna put an if and this is a double-headed arrow, that's if and only if. That means these two things are equivalent. The limit as x approaches x naught from the left, put a little negative. And the way to remember that is the negative numbers are on the left side of 0. So this is a left-handed limit of f of x equals L1, and that's also equal to the right-handed limit. So here I'm gonna write x approaches x naught with a little plus superscript. That means I'm approaching from the right side of 0. That those two values are the same. These are one-sided limits. This is a two-sided limit. When you don't have a little plus or minus here, you're talking about both sides at the same time, and they give you the same result. So, in other words, if I were to take, saying this, if I took the function f of x, and at x naught, I added a little tiny tweak, a little epsilon, and this epsilon is a small number, could be positive or negative, the output is approximately L1 for small magnitude epsilon. Okay, cool. Just making sure we kind of refresher of the one variable stuff. Is there any questions on any of this? This is the stuff that usually like people when they start Calc 1, it's like, oh my God. And then in Calc 2, you don't have to talk about it. You just have other things to worry about, like a lot of other things to worry about. Okay, so that's single variable limits. But what we're talking about are things like this. I've got a function of two variables, and I want to understand what it means to say the limit as the input point, this is a point in the plane, approaches some fixed value. What does it mean to say that that equals L? What does it mean to say that limit exists? Oh, and over here, this really quick, sorry, I forgot to say this part. So really quick, an example of a limit not existing would be this. If I had x naught here, and this was y equals f of x, notice that the limit from the left and the limit from the right are not the same, but I've only got two directions I can approach from, the left or the right. So here, limit as x approaches x naught from the left is not equal to the limit as x approaches x naught from the right. And so we say this limit does not exist. That's an important thing. So you got it, as you approach on every direction you can, and that's only two here. In contrast to here. Here, I've got, give me a second, let me get some surface going on here. Kind of bends through there a little bit, down. So this is z equals f of x. So I imagine some, funky s surface just floating in space there. And underneath here, I've got this point, let's make it right here, x naught, y naught, and that's this point right here. Is the picture making sense? Yeah, I don't need that shading or anything, we're good to go. All right. So what we're saying here is that as I approach this input value, it's kind of hard to draw, but let's draw a little circle right there. This function may or may not be defined at that value, but as I approach this point here, the output value approaches the level L. So this function right here, this would be that function value right there is level z equals L. Or just put z equals capital L right there. Now it might not make sense. Hopefully it still kind of makes some sense. I'm just saying the height of the points near that dot our height L. So that when I say this limit equals this means regardless of how I approach this point down here for input, the output value also approaches the input value. So, but think about how many ways there are to approach. There's infinitely many ways to approach that point. So that's the problem here. Here I only got two directions, and if my fingers don't meet from the left and right, then I can tell it doesn't. But here, I've got infinitely many ways to approach. So let's kind of get a more precise definition here. This means that we can get output values as close to L as desired by making the input values as close to X naught, Y naught. Let's see here, so as desired by making, I got a better word for it, making the input values, all input values, sufficiently close to the point where we're taking the limit. Now I kind of want to do some explorations with this, but first I want to put up one thing. This means that if we approach X naught, Y naught on some trajectory or some curve in the plane, on some plane curve, and here I'm going to put X of t, Y of t. So I've got a parameterized curve in the plane, and maybe it looks like this. Let's see. If this is, sorry Camila, I have a feeling like this is going to be hard to see. Do you want me to close the window? You got it? Okay, cool. Eric, you okay? Seeing that? Cool. So what I'm saying is we approach this thing on some space curve, parameterized space curve. So maybe that looks like this, X of t, comma, Y of t. And we're traveling toward it. So as we approach this point on any path that you can come up with, like that path could be a spiral in, it could just be a straight line in, up or down. The output value, and let's put this here, because now I've got some notation, f of X of t, Y of t approaches L. Now take a look at this, and then the thing I want you to notice is we took a thing that was a two variable X and Y input. Notice here this turns into a limit depending only on t. So the limit value depends only on t. So we can convert this figuring out what the limit is from a X and Y can be anything to I've got this curve that I'm traveling on and it depends on t, and then I plug that in over here, and now I've just got a limit of one variable, and this stuff all applies. Then it comes back to Calc 1. So this is back to Calc 1 limits. Let's do some examples, because this is all very abstract. So lots of cool stuff can happen. Could you please, if you have like your phone or laptop, pull up Desmos, please? Yes.
Would that be z equals fxy, or would it just be?
Not necessarily, because I didn't want it to make it look like, it would if this function were continuous and defined there and that hole were filled, but it's possible, Talon, that I have like, it's just like this guy that was here where it jumps up at that point, so I wanted to be careful with that. It's not about what happens at the point, just near it.
All right.
Okay, good question, really good question. So on Desmos, if, I don't know how you get 3D on the app. In the phone app, does it? Oh, like yeah, if you're using the web browser, you just put /3D I have the app on my phone, but I'm not sure how to get the 3D functionality.
I think it's just a different app.
Is it a different app?
You think so?
I don't know, you were saying it. That sounded like an Abbott Costello routine there for a minute. What were you saying?
I don't know if you can.
I don't know if you can either. Just go to the webpage, desmos.com/3D /. So, what I'd like you to do is enter in, you got your box there where you can put your function. Put this function in, x minus y over x minus 2y.
Let me see if I can look at lyrics here.
Okay, it looks pretty funky, right? That's not a glitch, no, it's just like it's a glitching out kind of trying to render it. Yeah, it's got those look cool, but that's a rendering glitch because the function's blowing up. So maybe zoom in a little by just, pinching and grabbing and zooming in as you normally would, or there's probably some zoom function. That actually makes it look a little bit better. But look at that weird surface. And what I want to think about in particular is, well, first off, let's look at some easier limits. Let's take a look as xy approaches 1, 2. Now on that graph, it's going to be hard to take these limits. But one of the things I kind of just want to point out to you right off the bat is just as in Calc 1, if you try to plug and chug the limit and it works, you're not dividing by 0, you're good to go. Dark secret. Unless the function, if you see an f of xy that's set up as a piecewise function, they're trying to rig it. That limit probably, there's something weird going on with that. But if you have a function like this, where we have x minus y over x minus 2y, your first attempt should be plug and chug. And so I'm going to put here, plan, plug and chug, whatever that means. It means plug in the limit and see what you get. So here I've got x equals 1, y equals 2, I plug that in, I've got 1 minus 2 over 1 minus 4 equals negative 1 over negative 3 equals the curvature of that thing you just did. Last week, the kappa was 1/3 on that curvature problem. So that's pure coincidence. This is the limit. So I could say here, this is 1/3. And if you looked on the graph and you could somehow get on the input and output values where we had 1 and 3, and then you went up to that surface, you would see that that surface has the point 1, 2, 1/3 on it. You can see that. You're all good. The only place this function is going to have trouble is when. When are we going to have trouble? What points would be bad to put in here?
Zeros?
0 for sure. Anything where the denominator is 0, where is that?
When x equals 2 and y equals 1.
That's definitely one of the points. Are there more than one place where this bottom goes bad? Yeah, there's a whole freaking line, right? So notice here, notice that the domain of this function is equal to all xy points as long as x isn't equal to 2y. As long as that's not happening, and that is a line of slope 1/2. So in the xy plane, our domain, our list of values that are good are everything except y equals 1/2 x. So if I plug something like that in, this function is going to be bad. And you can see it, right? It's blowing up. You've got this asymptotic wall in the function. Are you seeing it there? It's kind of like this sheet that's like shooting up to infinity. And then I think on the other side it probably goes down. So you've got something like, it kind of looks like something like this. right? There's like this one sheet that's shooting down and this one sheet that's coming up, and then they're joined somehow weirdly in the middle. Is that what we're seeing? Okay. So, we know that this thing isn't defined here. We wouldn't take a limit at a point that's not, well, we might, but we're not going to. Because along here, if I take points that are in this region, x equals 2y, it's either gonna go to plus infinity or minus infinity, whether you're on this up wall or this down wall. And it kind of depends on how you approach that line as to which side you're gonna go on. But let's take a look at something else. What if I approach on a different route? So what if I approach 0, 0, which seems to be a pretty bad point, right? That's literally 0 on top, 0 on the bottom. So note, bless you, f of 0, 0 has the form 0 over 0. Is 0 over 0 form. That's an indeterminate form. That's bad news. But that means your limit could be anything. So in this stuff here, the next part of my plan is to, if we get 0 over 0, we need a deeper analysis. And it's likely that the limit does not exist, especially in these multivariate ones. And that's what I got here. I've got 0 over 0 in this limit as xy approaches zip zip of f of xy. So I'm going to give us a problem. We're going to find that limit or find that it doesn't exist. If it exists, it shouldn't matter how I approach 0, 0. So let's look at the top view of the plane again. So here's x, y. These are my input. This is my input values. I'm not going to be on this line here because I don't want to be where nothing makes sense. But I might want to approach on, let's say, y equals negative x. So let's approach 0, 0 on the line, move it up this way, y equals negative x. Now the thing you have to do here is kind of parameterize the curve. So I need a parameterized version. Of y equals negative x. And to do that, don't think super hard, just pick an x value, I'm going to call it t, and then what would the y value be that makes sure I'm on there? If x is t, what is y?
Negative.
There you go, negative t. So this is my parameterized curve right here. So I'm going to let x equal t and y equal negative t, i.e. let x equal t and y equal negative t, and plug those into the function. And consider f of t comma negative t. And when I do this, now I've got a function of one variable, and I can compute it. It's going to be, what do we got? We've got x minus y. So again, here's x, here's y. So I've got t minus negative t, x minus y, over x minus 2y. So x minus 2 times whatever this y is here. So look what I got. I got 2t, t plus t, over 3t. And when I think now about the limit of this as t approaches 0, I can find it. What is that limit? Well, you plug in 0, 0, right? Doing the plug and chug method, what do you get when you do plug and chug? 0 over 0. What kind of moves could I make to find that limit? In other words, as t approaches 0, what's this limit? Somebody give me one route. What's that?
Can you do L'Hopital?
Could totally L'Hopital, absolutely. We still got all that stuff. It's 0 over 0. So I could, thanks to Camila, do L'Hopital's rule. So L'Hopital means take the limit as t goes to 0 of the derivative of this with respect to t over the derivative of this with respect to t. Now there ain't no more t's. So the limit's 2/3. What's another route we could have gone? Cancel out the t's. That's the other route. So here, I could have just canceled out the trouble, and notice I would have got 2/3 as well. Just be careful with your canceling. I've seen some funky stuff happen occasionally. So the limit is 2/3, even though it looks like the limit doesn't exist. Let me ask you a question. Please find the limit. So right now, we've got approaching along this line, the limit equals 2/3. Let's approach along a different line. Let's approach along a simpler line. How about just the x-axis? So now let's approach along the x-axis. So now approach along the x-axis. What does that look like? That means I essentially just have y equals 0 and x is free. So all the points on the x-axis just look like this. Does that make sense? Or I could make it look like points like this, t0. So for any t, this is on the x-axis. How would I parameterize the y-axis?
Yeah, like same way, but like flip it around.
0, t. Those are good things. Let's put up some common, because you're gonna want these, common parameterizations. Along the x-axis, which is what we just did. Along the x-axis, you're gonna use t, 0. That means your x is t and your y is fixed at 0. Along the y-axis, we've got 0, t here. I'm going to replace the x with 0 and the y with t. Let's do along y equals x, the diagonal, the perfect diagonal. One of the perfect diagonals. I'm just going to use t, t. Along, and these are good to have just ready. Y equals -x, we already did that. T, -t. I want to do one more funky one that you might need. Along y equals x². So think about what that is. That's approaching along a parabola. And that is just t, t².
Why is it not the square root of t?
Because I want t to be a negative number possibly as well. So here t would be less than 0 and here t would be positive. Does that make sense? And I want to be able to get both approaches. Good question. Okay. So what is the limit? And we just did it here. Find the limit along the x-axis. As you approach along the x-axis, do that for me, please. And then, well, you know, while you're at it, just to get practice, along the y-axis. So that's approaching this way. First one's approaching this way. What do you get? What's that first one simplified to along the x-axis? We got, see, let's just make sure, let's go through it just to be safe. I'm letting x be t, I'm letting y be 0. Get this? 0, doesn't matter, I've got t over t. Let's cancel the t's, we get 1. So along the horizontal axis, the limit equals 1. We already know the limit doesn't exist. Because approaching on this line, we got 2/3. Approaching on this line, we got 1. Since those two approaches give different results, the limit does not exist. But for just fun, let's approach along the y-axis just to like get the practice of it. So here I'm gonna let x equals 0. The x coordinate is fixed at 0. The y coordinate is gonna be my parameterized thing. So when I replace 0, then x minus 2y over x minus y over x minus 2y becomes 0 minus t over 0 minus 2t. And do you see that there I'm going to get 1/2? Make sure you see that. I see some people nodding. Tell me if you need me to talk about that or we feel okay. So look at this. We've got another new answer. When I approach along this way, along the vertical axis, I get the limit is 1/2. I will tell you right now, you give me a number you want the limit to be, and we can find a line that does that. It's pretty crazy. It's pretty wild. Just think about how that thing's asymptotic though. We're just kind of like shooting up and down different parts of that weird infinite sheet. Does this sound okay? So let me give you one to ask. So final conclusion is limit does not exist. I don't even know where I put the original problem. So here's f of x, y equals that. So here I'm going to say limit as x approaches, x, y approaches zip, zip, of f of x, y does not exist. And I would say because that. All right, I got a funky one in my notes for sure. I want to make sure I get it right. I noticed they gave us a clock after I bought a clock. I guess start watching the stuff I say in here. We had a department meeting where I'm not supposed to say certain things in here, political things. So I need to stop doing that.
The clock political?
What's that?
Is the clock political?
The clock, no, but I've
It's got a microphone on it.
Yeah.
I kind of, yeah, I never even thought of that. Let's smash that clock. I've been just, I don't want to complain about anything. Not while I document it anyway. Yeah, so how about this one? This last one, and then we'll kind of move on. So, find or argue that it doesn't exist. Actually, I'm going to give you two of them. Okay. So, y equals, or limit as xy approaches 1, 1 of x squared plus y squared over x to the 4th minus y squared. And actually, let's make this one different. Make that a 0, 1, 0. Okay. Yeah. And let's make that y, sorry, make that x to the 4th also up on top. That won't change what you're doing right now. Let's try this guy.
That's the minus, right?
Yes, sir. It's a plus on top and a minus on the bottom. Oh, man, yeah, whatever, let's just keep doing it, it's not the problem I wanted. Maybe it is, I don't know. Guess we'll see. And then the other limit that I would like you to think about is this one, this super troublesome one. So I'll just tell you the second one doesn't exist. Find two different approaches that get you different answers on this one here. Well, what about this top one? What do we get?
Just one.
Just one, yeah, because you plug, this is like a plug and chug one. You plug it in, you get 1 to the 4th plus 0 squared over 1 to the 4th minus 0 squared. That's just one. So that one definitely exists in like the nice simple way. And if you want to get funky, I guess what I was thinking about is that bottom parameterization I gave you. You could try that one here. That funky parabolic approach, just to have some fun, just to be like spicy. But there's easier approaches. Continuity is not going to take long. There's usually some super low hanging fruit with these, like along the x-axis, along the y-axis, along some line of slope M. Those are always good bets. But if you wanted to get, like I said, spicy, try it along that parabola too. Because it's kind of interesting that you get a different answer on that parabola. The example I wanted was one where no matter how we approached, if we approached on straight lines, we got the same answer. But when we approach on a parabola, we get a different answer. This ain't that, unfortunately. So on the x-axis, you should be getting 1 on this one. And you should get -1 on the y-axis. And this one should be cool. Oh, damn it. Sorry, well, it's okay. It's not okay. I'll come in with a better one. I'll do my work ahead of time better. What's this? This is just garbage, right? This is just like something divided by 0. We know that's bad. Sorry. I'm sorry. I am really really sorry, because I wanted something cool to happen. That's what happens sometimes. So do we see that this limit doesn't exist despite it? Like, we took the low-hanging fruit routes, these were way better. Okay, cool. So because we got two different limits approaching 0, 0, limit does not exist. Cool, let's move on. I'm gonna knock out continuity pretty fast, because in the, oh yes,
So,
sorry.
if you, like, if along the X and Y axis are the same, is that enough to say that the limit exists? Or do you?
Oh, what an awesome question. Absolutely not. So part of the problem, and that was what I was hoping this example would do, just simply demonstrating that it's good along the x-axis. Oh, I got 3. Oh, I got 3. Oh, I got 3 along every line. That's still not enough. So I'll come in with an example where no matter how we approach, if we approach straight, we get the same answer. But then if we approach on the parabola, we get a different answer.
Okay,
And I'll like try to get one of those out for you.
okay.
Does that sound cool?
Yeah.
Yeah, so these are really, honestly, it's easier to show the limits do not exist than they do. We don't even have the math tools at this level to show the limits exist.
Okay,
It takes a lot heavier tools. So don't worry about that.
okay.
But that was an awesome, thank you for actually raising that point. That's an amazing point. Cool. Okay, so let's talk about continuity. We say, oh, and by the way, all this stuff can happen in many dimensions. So in this one, you're approaching things in 3D space. So imagine you've got a point in space, think of all the ways there are to approach a point in space. A lot more than even in the plane, but it's still infinitely many. And it's as tricky as Daniel said, this, like, showing this limit exists is about as hard as showing it here, but we can't do it yet. So we would say that a function f of xy is continuous at a point. And it's always been a point of amazement to me that we talk about continuity at a point. Because we think of continuity as this, like, right? There's no breaks, and I'm thinking about traveling. But continuity is a local condition at points. So we say f of xy is continuous at a point, x naught, y naught, if the limit as I approach that point of f of xy is equal to f at x naught, y naught. Now there's 3 things here. There's 3 things, conditions is the word I'm looking for, that are packed into that statement, that are hidden. So let's talk about them. First off, to simply write this expression f of x naught, y naught, means the function is defined at that point. It means I can actually compute this value. So 1 is writing f of x naught, y naught means f is defined at that point. It's not just an asymptote, there's not just some hole there where it's just not defined. So there's a value, there's a point above that is on there. There's an f of x naught, y naught, there's a place I can go that corresponds to those input conditions. 2, writing limit as xy approaches x naught, y naught of f of xy equals something. It doesn't matter what's over there. Simply writing that something means the limit exists. So the fact that I'm writing that equals something says that no matter how I approach this point, I get that same value out. So this means the limit exists. And then 3, saying that the limit is equal to the value of the function there means that the value at that location is actually equal to the values near that location. So 3, saying lim, getting old writing it, x naught, y naught, f of x, y equals f of x naught, y naught means the limit value is the same as the function value. It's the same as the function value. So I'll draw a little picture. I've kind of already drawn one, but so you can see what I mean. It's not happening. So what's not happening is this. Got my surface. It's a little Pac-Man thing or something. I don't know what that is. But let's say it comes, ooh, that helps. Oh, that actually helps. Let's do this too. That helps too. Kind of make it look like they're puncturing, the axes are puncturing the surface. So what I'm saying is that, and then these are hidden back in there. Those are hidden. So at x naught, y naught, the value of the function, if I go up to it, there's not some hole there, and then somehow the value of the function rises above the surface. So if you're having trouble picturing that, what I'm saying in 2D is this doesn't happen. So if you look at maybe a slice from the side, I'm saying that doesn't happen. That here the limit exists, because as I approach from both sides, my fingers meet, I approach the same value. Function is defined, and it didn't fill the hole. That means it fills any hole that could possibly be there. So not this. That's enough with continuity. Let's just talk really quick. Most stuff is going to be continuous. Anytime you can plug and chug, and it's not a piecewise defined function that looks like it's trying to set you up for trouble, it's continuous. So how do we know what's continuous? Well, let's just make a list of some things. So how do we identify, in the wild, identify continuous multivariate functions? As long as you're avoiding a quotient, you're probably fine. So anything that's a polynomial is going to be totally good. So all polynomials are contiguous everywhere. So for example, if I have x squared y cubed minus 2xy to the 7th plus 3. That's a polynomial in 2 variables. That's continuous everywhere. I don't have to worry about dividing by 0. So the only time you have to worry about continuity is when you are doing division. Trouble arises when we have quotients. But frankly, everything, even if it's a quotient, it will be continuous on its domain. So trouble arises when we have quotients, but they are most likely continuous on their domain. Let me give you an example of somebody trying to trick you. Let's see what it looks like when a textbook or a quiz or whatever is trying to toss you off your guard. So example, is f of xy equals, now there's trouble instantly, because I'm about to do piecewise. So you know there's trouble. Let's go back to x squared y cubed minus 2xy to the 7th plus 3 if xy is not 0, if we're not at the origin, and it equals 2 if the input is xy, or is 0, 0, excuse me.
I think you forgot the not symbol on the top one.
Thank you. Forgot.
One of them.
Oh no, I think this. Oh yes, thank you. Yes, thank you, Daniel. Yes, absolutely. Yes, one of them. One of them needs it. That's what I mean. Thank you. Good stuff. So this is saying that if the input is anything but 0, use this formula. If the input is 0 and 0, use this formula. So let's really quick, let's just do this limit. Limit is xy approaches 0, 0 of this weird function. Well, limits aren't about what happens at the point. So this xy is by definition not equal to the 0, 0. So note, here xy is not 0, 0 because limits aren't about being at the point. So I'm going to use the top definition. And I'm basically going to take the limit of this thing as xy approaches 0, 0. If I said, hey, find the limit as x and y approaches 0, 0 of this, what would you get?
3.
3. Just plug and shove. Plug in 0, x, 0 for y. So this limit is just 0 squared, 0 cubed, minus 2, 0, 0 to the 7th, plus 3, and that's 3. But what is the value of the function at 0, 0?
It's 2.
2. So this function isn't continuous at 0, 0. But it is everywhere else. What happened is some trickster took the point at 0, 0 and moved it down 2 units below the surface, or 1 unit below the surface, because it just dropped 1. Took a little ice pick. Yeah, I know, shake your head, trouble. Okay, so continuity, most everything will be continuous, you'll be fine. I got 15 minutes to get to really what I wanted to get to today, unless you have any questions on that. Because here's where calculus starts up again. It's been a while. I guess we had calc with the arc length, but not full calc. Even there, I didn't ask you to do the integrals. So let's talk about derivatives of these multivariate functions. Now it's going to get fun again. Now calc is back. Sometimes people feel a lot stronger at calc than they do at like algebra and things like that. That is not a weird occurrence. So these are called partial derivatives. And these are just derivatives of multivariate functions. And I'm kind of just gonna I'm just gonna get to the heart of this. If I have this function f of xy, I can treat either of these quantities as the one that's moving. So basically what we're going to do is calc 1 on these functions. We're just going to keep the eye on only one variable at a time. So if I say, let's find, now notice the new symbol, that is called a del symbol. It looks like a D. It's not, you kind of stop a little short. Maybe they do sometimes close it off, but that is del, it's not D, over del x. Now this symbol right here means partial derivative with respect to x. And what that means is treat y as a constant. And this just takes a little practice. If you've never done this, you'll get good at it, because it's just like derivatives. you're used to taking. I've seen lots of derivatives being taken quite well in here. Everybody kind of rocked the derivatives on the arc length thing, so I think we've got that. So this is, here's a new notation for it. I could also write f sub x of x comma y. That just means partial with respect to x. And let's actually get the definition up just so that we have it and we've seen it. We can say that I wrote it in case I get sued. So this is limit as some small quantity approaches zero, some h. And I'm only going to take the derivative on the x. So it's x plus h comma y minus f at x comma y over h. See, it looks just like a normal derivative. You just got this little extra y in there. And then we've got the partial with respect to y. And that is denoted f sub y of xy. And let's just get it up here. This is the limit as h goes to 0 of, now I leave the x as the constant. So now I'm treating y as the variable quantity and x as the constant. So again here, treat x as constant. Take the derivative on the y. And now we're just going to practice this a bunch. Because we got 10 minutes left, 11 minutes left, we can do a lot of practice. So examples. Find the partial with respect to x of, what was that stupid, Daniel, can I look in your notes, that polynomial I had before? There he is. Oh, I think he was down a little. That guy right down there.
This guy?
This one here. Yeah, I don't want to do that
this
quotient rule yet, no.
X squared y cubed
X squared y cubed.
minus 2xy to the 7th.
Thank you. And then it was plus 3. Yeah, cool, thank you. So let's do that. So I say, take this partial with respect to x. See, sometimes my partials look like 2's. I can't wait till I see yours, Othman. I can't wait till I see your del symbols, man, because like, you got, like I said, you got some style. I have to show you all someday. I don't know, you might be embarrassed by that. You shouldn't be. They're beautiful, beautiful numbers. So, here we're gonna treat the x as the variable, the y as the constant. So that means this is like a 7 here. And I'm just gonna forget about it. I'm gonna differentiate the x and let the y follow along. So 2xy cubed, didn't touch the y stuff. Just treat it as a symbol that is constant. And then here, derivative of 2x is 2. Leave the y to the 7th alone. What happens to the 3? It just goes away, it goes to 0. There's no x or y, and it's constant with respect to both variables. So do me a favor and find the partial of that thing with respect to y and test yourself out, see how this is going for you. You okay, sorry?
Oh, yeah.
Yeah, okay, cool. Christian, what'd you get?
In terms of y, I got 3x squared y squared minus 14xy to the 6th.
Beautiful. How do we feel about this? And I like how you pulled the constants out in front and just kind of reorganized it. Yeah, notice how he took the derivative of y cubed was 3y squared, and he just pulled it out in front. That's the pretty way to do it. Here we took power rule, derivative of y to the 7th. 7 comes out front, 2 times 7, 14. Decrement the exponent, and then 3 goes to 0. Beautiful. Is there any questions on this? How are we feeling? We're feeling like a challenge. Outstanding. No. No, come on, you got this. And I thought I was gonna have like a haircut and trim my beard today, cause over the weekend, last weekend, my wife was like, "Hon, you need to get a haircut and you need to trim your beard." She said, "I feel like I live with Santa, like hobo Santa," you know, like, and she wouldn't have a problem saying that. And like, once my wife starts saying like, "You're getting a mullet," or whatever, it's just like, okay. But I didn't find time yet, so maybe on Friday.
Do the mullet.
What's that?
Do the mullet.
Try it out.
The mullet.
The mullet, oh, the mullet?
I know.
I've had those in the, I mean, like, I grew up in mullet time, right? I was in the Midwest
You have to show us a photo.
in the 70s and 80s. Yeah. Yeah, we lived in mullets. Now they're cool. I don't know if they're cool. I don't know if they're cool, but they're a statement, right?
Yeah, we have lotion by
Limit. Oh, whoa, easy, buddy. Let's just say f of xy equals x plus y over x minus y. Find partial of f with respect to x. Find partial of f with respect to y. Be careful. What rule do we need? Quotient rule. ODI. Yes, that thing. Okay, give me flashbacks to my calc class. I had this 100-year-old woman from Kentucky who taught me Calc 1. Yeah, and she would high for holy low. It was awesome. She was great. She was a great lady. Really good teacher. One of those teachers who's just like you, they're not gonna leave the classroom till it's the end days, you know? You probably want to simplify. Eventually, you're really going to want to. Did I get it right? We've got some agreement. You good, Kayla? Or did you get the double negative get you or something? Or
I just like, I don't know why I was thinking it would be y, but it's a constant, so it disappears.
Awesome. Yeah, good. Yeah, good. Does everybody see why the derivative of the numerator is 1? Derivative of x is 1. Derivative of y, 0 with respect to x. Yeah? Anybody need extra explanation? I'm happy to. And the derivative of the denominator is 1. And this is the minus that comes from the quotient rule, right? That came along for the ride from the rule. So I'll do this guy then next. This one's got a little bit more of an interesting twist, but go ahead and I will silently work it through. Just use lots of parentheses, take your time. An extra line can save you a lot of grief down the way. You see this is like there's kind of a beautiful symmetry, right? There's that 2y up there, negative 2y, there's a 2x in the bottom. You're gonna see that beautiful symmetry a lot in these kinds of things. Got time for one more, but I'll happily entertain any slow walkthroughs here that we need. Are we good? Okay, I'm not seeing any people telling me to do otherwise, so let's see, I think I came up with a couple fun ones here. Yeah. Please find all the partials. Yeah. We'll probably practice. This is probably Friday's thing. We're gonna do a lot of derivative practice and get really good at it again. And these are just chill. There's no like product rules. There is a chain rule here on that YZ, so just be careful with that. And you are probably going to want to bring your derivative tables in from now on, just to have those by your side. Because I will start pulling out weird shit. Today I'm just being chill, but if I asked you what the derivative of arcsecant was, might wish you had a table, right? Yeah, yeah it is, yes. Yeah, it is 1 over square root or something. 100%, totally, yeah, you got it. Let's see here, some constant. Here's a couple special cases. I think I put these up early during the review. I put up some special cases of the chain rule, and those are really going to help you for sure. Having those just around that A is a constant, and so is Y. Right? So having these at hand, and I was pretty kind. Then I wished I hadn't been, but I didn't put a Y up in the exponent of the E. But I guess we don't have time for anything cruel. So for this one, the E to the X is a constant. Derivative of cosine. Look, I'm using that rule there. Here, the A is equal to the Z, and the Y is the X. So that derivative of cosine of YZ, first I do the derivative of the outside, leave the inside alone, times the partial of the inside with respect to Y, and that is just Z. And then you could rewrite that, make that way prettier like Christian did earlier on. I would pull the minus out in front at a minimum. And then this guy, kind of the same game, except now the Z is the moving part. So we've got negative sine of YZ, derivative of YZ with respect to Z. Y, absolutely. We'll play more. We'll play more on Friday. Thank you, friends. Send me, if you want to come in tomorrow, like I said, I'll be in right around a little before 10 if you want to start then with me. Otherwise, tell me when you can make it and I'll hook you up with Cybert or somebody. Okay? Because all I have to do is give you something. But I have to print it to give to them.